Hi, this is going to be a unit on implicit regularization. So far we've talked about preference for one model over another. And in the free lunch theorem, we talked about the complexity of a model. How many bits does it take to name a rule or a classifier? And the idea was that simple rules that do well on training data will do well on test data. In implicit regularization, we sort of turn this around. Instead of asking what's our a priori bias, what models or rules do we prefer a priori, like the simple ones, we're going to look at a learning algorithm and see if the algorithm, by virtue of its structure, has an implicit preference for certain models, an implicit regularization or learning bias. So this is sometimes called implicit bias. Unfortunate choice of words. I'm going to call it implicit regularization. So a particularly simple or at least analyzable example of this is support vector machines and their relationship to linear regression. So if you consider a least square regression, where you have many more features that you're regressing onto, many more covariates than data points. So the model space has many more degrees of freedom than the number of training points you have. You can always fit the data exactly. And furthermore, there are many different settings of the weights in your model that will all fit the data exactly. And the innovation of support vector machines many years ago was to say, well, we're going to impose a bias where we minimize the norm squared of the weight vector that we assign to the features, to the covariates. And so this was the basic idea behind support vector machines. You get a minimum norm weight vector that classifies the data. Now, in least square regression and support vector machines, there is a closed form solution for that learned weight vector, but you don't have to do it that way. You could do it by, for example, stochastic gradient descent. So if we take the least square regression problem and just define the square loss and start doing gradient descent on that, it's a convex problem, and if you let the learning rate go to 0, you will converge on a solution. Now, it turns out that when you do gradient descent on the least square error on a training set, that your weight vector is always, it's an invariant of that algorithm. That algorithm preserves the invariant that the weight vector is some linear combination of the feature vectors of your training points. And it's a theorem, a true fact, that if you find a linear combination of your training points that exactly fits your data, it is the least norm solution. So it is the support vector machine solution, but it comes out of the algorithm. So the minimum norm property or assumption behind the support vector machine arises from the algorithm. I just said this slide. Linear regression converges to a minimum norm solution. So that's an example of implicit regularization. Implicit in the SGD algorithm on that loss is the minimum norm property. All right, I've just got ahead of myself in the slides. I'm going to skip to the next slide. Does this work for stochastic gradient descent? So stochastic gradient descent is kind of mysterious in how well deep models generalize. Is there a theory, a general theory of implicit regularization that can be applied in principle to sort of any algorithm, to stochastic gradient descent in particular? So I'm going to look at stochastic gradient descent, and I'm going to construct a packed Bayesian analysis of implicit regularization. I'm going to do it in a way that applies to basically any learning algorithm. But I'm going to use SGD as the first example. So let's go back to the beginning. So I've got some model, right? This is a deep model. The deep model defines a probability over some label for some input. Let's say we're labeling images. So this P phi is our model. Given a parameter setting phi, this P phi gives us a loss, right? The log loss is minus log probability of y given x. And we want to minimize that over, want to minimize the expectation of this over draws of x, y. And that's what we're going to do gradient descent on, is the cross entropy loss. Just what we've been doing all along. Okay, so I'm going to write SGD. SGD is going to take this model. It's going to use that to compute the loss gradients. I'm going to fix an initialization. That's going to greatly improve. If I fix an initialization, it's going to improve stability. I'll talk about that in a minute. And then this algorithm is going to take some training data. And I'm going to fix all the parameters. So I'm going to fix the hyperparameters, the rate at which the learning rate is reduced, the number of iterations or epochs, so that this becomes a deterministic. So I'm going to get it deterministically a vector as a property, as a result of running SGD on this model and this initialization and this training data. I'm even going to fix the order in which I visit the training points. But then, since we're learning a point in a continuous space, we have to use the Pac-Bayes version that's capable of handling continuous spaces. And we can do that by taking the parameter vector we learn, the result of SGD, and adding some Gaussian noise. And when we add some Gaussian noise, that's intuitively like limiting the precision. We're losing information in the real numbers generated here when we add Gaussian noise. So it's like losing precision. So it's almost like, you know, having finite floating point numbers. But it's standard practice to just use this noise and use the Pac-Bayesian theorem and continue to work in the continuous parameter space. Okay, implicit prior. So we're going to define a prior or a learning bias. In the Pac-Bayesian framework, you have this arbitrary prior probability where you're not assuming any truth to the prior. Given an algorithm like this, I'm going to define an implicit prior defined by the algorithm. It's really going to work for any algorithm. So the prior probability distribution over the vectors is going to be defined in terms of the model, the initialization, and the population distribution. So so I'm going to define this in terms of the population distribution by saying, well, this prior probability over the model parameters, this is a very strange thing. This prior probability over the model parameters is the average, the expectation when we draw training data of the probability that the learned model that I get from that training data and then add noise to gives me this vector. And this is also a density, right? Because I'm adding smooth noise. So this is sort of the probability of getting this vector when I draw training data. So it's defined in terms of the population distribution. So it's the probability of this vector when I draw training data, run the algorithm, and draw a vector from that algorithm by adding noise, this is the probability that I get this vector. And the point is that this distribution is defined independent of any particular training data. So it's impossible that this distribution is fit to any particular training data. It's fit to the population distribution, but that's okay. And it turns out that this is a perfectly legal prior in the Pac-Bayesian guarantee. So this is an implicit prior. It's defined by the algorithm. So let's do I'm going to just write the guarantee in the general case. So I'm going to let A, just a generic A, be any algorithm that maps a training set, train, to a probability density. I'm going to write this probability density as Q sub algorithm and train, and it's a density on this parameter vector. I'm writing a prime there because in the previous model, we did a deterministic phi and then we added noise to get a phi prime. So it's the phi prime that has a continuous density. So the algorithm A in the training set is going to give us a density on phi prime. And then the implicit prior defined by algorithm A is just what I defined before, but now I'm just doing it in general. So the prior for algorithm A defined in terms of the population, this prior density on phi prime is the expectation when I draw training set of the probability of that when I apply the algorithm to that training set. So it's the expected probability that you get when you run on train. Okay, now I can just, the packed Bayesian bound is just going to apply. So I'm going to define the loss on the population. Okay, so what's happening? I'm drawing training data. I'm running my algorithm on the training data. The algorithm on the training data is giving me a stochastic classifier. That stochastic classifier may be overfit to the training data. But what I really care about is what this stochastic classifier does on test data. So this is the test data loss. So this is the average over drawing new data from the population and drawing the model parameter from the distribution learned on the training data. So this, you draw the model from what you learned, but you draw from the population and you take the loss. So that's just what we've been doing before. This is, you learn an algorithm, but what you care about is how well it does in the population. There's also a training loss, right? This is the thing that you sort of heuristically optimize during learning. So this is the average when you draw from, this is the average over your training data when you draw from your learned model of the loss on the training data. So you're always training on the training data, but the thing you get from the training data can be measured on the population or measured on the training data. And overfitting is when the measurement on the training data is much better than the measurement on the population. But the packed Bayesian bound now is going to apply because it applies to any prior. There doesn't have to be any truth to the prior or belief in the prior. The only thing you need is that the prior doesn't depend on the training data. So what we get is that with probability at least 1 minus delta over the draw of the training data, we're going to have that the generalization loss of whatever this algorithm learns. Remember, we're just fixing an algorithm and we're fixing a population. The test loss of whatever this algorithm learns, this is the test loss when you learn an algorithm on the training data, is we're applying our standard formula, is a number near 1 times the training loss of that algorithm, of the result of the running the algorithm on the training data, plus the standard multiplier. And this just becomes the KL divergence from the learned distribution to sort of the average distribution on the population. And you can, there's a fairly simple theorem that given this algorithm that's returning these distributions, this is the prior that minimizes the expectation of this KL divergence over drawing training data. So in some sense, this is an optimal prior for this algorithm. So we've turned things around, right? Instead of saying, what's our prior belief? Given our prior belief, we'll design an algorithm to do something like a posterior, something like a Bayesian posterior. Even the packed Bayes has that kind of feel. You pick a prior, pick some notion of simplicity or bias, and then you optimize a trade-off between simplicity and training loss. Here we say, oh, I could fix the algorithm, and from the algorithm extract my bias that's implicit in the algorithm. So this is this is a general implicit regularization theorem. Okay, and I'll stop there. Thanks.